Hi, this is Simonas. In today's video, we will look at wide-range inversion routine, a data evaluation procedure to obtain extended particle number size distribution from measurements performed by both mobility and aerodynamic particle size spectrometers. As this procedure is somewhat similar to regular inversion routine, please refer to our previous videos for more details on how to run inversion in general. With that being said, there are several differences which have to be mentioned. To run the wide-range inversion, you will need a custom-built software, which is not freely available, however, could be acquired on request. As in regular inversion procedure, we have to first copy all the necessary files into working directory. This includes .diagnostic and .raw files from MPSS as well as files from APSS. Please note that file format from MPSS raw and APSS DAT files must be identical, meaning that not only the file format must be the same, but also the timestamp should match perfectly. In other words, one MPSS scan should have corresponding APSS scan. In case APSS was logged separately, it might require some initial preparation to match the files, which we will not cover in this video. It must be also mentioned that unlike in general inversion routine, wide-range inversion is highly suggested to perform for each separate MPSS and APSS scan. This is because in the inversion routine, you will be asked to provide bulk aerosol particle shape and density. Therefore, unless we have a strong basis to believe that particle shape and density does not change over the time, the best results for wide-range inversion will be achieved by processing every single scan separately. For the purpose of this demonstration, I have prepared two cases: a file with several MPSS and APSS scans, and a file with one scan only. In reality, MPSS and APSS will generate one file per day, which will contain 576 lines if time resolution of MPSS scan is set to 5 minutes. This means that you have to prepare 288 separate files for MPSS raw, 288 separate files for MPSS diagnostic, and 288 separate files for APSS data. Averaging several scans, for example to 1 hour time resolution, may help to reduce the load. Similar to general inversion, the procedure can be performed for multiple measurement days simultaneously. However, the assumption that particle shape and density did not change over the hours of day and multiple days must be valid. Prior to the inversion routine, we have to set the configuration file. Please refer to our previous video on general inversion routine for more information. In case of wide-range inversion, the only difference in configuration file is the additional fields of external raw size distributions and external size distributions after inversion, which in regular inversions ini file are not present. Additionally to MPSS diagnostic and raw files, we have to define the APSS file. In external raw size distribution row, we have to define the prefix and file type of APSS file. For an output, we want to choose level 2 and external size distribution after inversion for MPSS and APSS files respectively. To do this, we have to type on near the corresponding fields. The rest of the configuration file is identical to that of regular inversion. Please refer to previous video for more details on how to fully prepare the configuration file. When the configuration parameters are finally set, it is important to save them as txt file, which can then be loaded into inversion software. Give me a second to do that. Now we can open the inversion software. I have to mention that to run the program, you will need LabVIEW runtime engine. For more details, please refer to internet page. When you first time open the program, you will be greeted with an error. Like in general inversion, this is because program tries to execute with the default parameters, which for our case of course are incorrect. Just click stop to bypass this issue. At first, we have to set the path to our prepared ini file, which will take care of the rest. We need to give the full path with ini file name. Give me a second to do that. When this is done, you may choose to turn the file list option to on. In this way, you will be allowed to choose multiple files for the inversion procedure. However, as I already said before, unless particle shape and density is expected to stay constant over the multiple days, I recommend to run inversion scan by scan. For this, I will leave the file list option off. To proceed with inversion, we have to manually enter the file name into File Progress Indicator field. For demonstration purposes, I will start with a file containing multiple size distributions. keeping in mind our predefined file names, I will load in 15 tag1 file. We can now press run arrow to see whether the configuration file is loaded and everything is okay. Please note that at this point, we do not care about particle shape and density yet, and run the inversion to see whether the configuration file was prepared correctly. We will take care of this later. For now, we can see that any file was loaded successfully with no errors. In Save Output field, .in2 and .ap1 output files are highlighted. In the particle number size distribution field, we can see multiple lines representing multiple measurements in loaded files. Wide-range inversion shape and density parameters can be found on the most right of the software window. In the right bottom corner, there is a graph that represents both MPSS and APSS particle number size distributions after the inversion. It is possible to adjust graph axis for better visualization. Give me a second to do that. Now comes the fun part. By playing with shape and density, our task is to find the parameters that result in the best fit between MPSS and APSS particle number size distributions. Here, size-dependent particle shape and density are expressed by the error function. The easiest way to explain the meaning of these values is by using the sigmoidal curve. The first two values describe how function responds at 0 and infinity. Third and fourth values represent inflection point and slope factor. For example, in our case here, the shape parameter is defined by the minimum and maximum values of 1 and 1.1 respectively. The center of S-curve is at 700 nanometers and the slope factor is 400 nanometers. By increasing the slope factor, the transition speed between minimum and maximum shape factor decreases. That is, the transition from 1 to 1.1 happens slower. And vice versa, by decreasing the slope factor, the transition between 1 and 1.1 happens faster. The same line of thought applies for particle density. Although all parameters are free to choose by user, values from literature could be a good starting point in performing the inversion procedure. For example, in our case, aerosol particle number size distributions were measured at the roadside in Metro Manila, where the black carbon mass concentration is extremely high. Therefore, we would expect particle shape factor to be between 1 to 2.4 with a transition region at 100 nanometers. Likewise, particle density in grams per cubic centimeter, we would expect to vary between 1 and 2.2. When shape and density parameters are set, we can run the inversion routine by clicking Run arrow once again. Program will automatically provide inverted particle number size distributions for inspection. In our case, we can see that with our chosen particle shape and density, the MPSS and APSS particle number size distributions overlap reasonably well. In case the transition or overlap between MPSS and APSS particle number size distribution is not reached, you may want to tweak the shape and density parameter. However, please make sure that the values stay in physically meaningful range. Now, let's look at a different case when we run one distribution per file. To load it, we type its name in the progress indicator field and press Run arrow. From the very beginning, we can see that the shape and density from our last run fits reasonably well, giving us a smooth transition between MPSS and APSS particle number size distributions. Remember, you have to click Run arrow after making any changes. At this point, we are done, and the inverted distributions are stored in the working folder as .in2 and .ap1 files. The next step would be to merge the inverted particle number size distributions from both MPSS and APSS. This would require deleting several last points in MPSS distribution and some of the first points in APSS distribution, as well as refitting the obtained size distribution with the spline curve for smoother outcome. Before we finish this video, I would like to make some notes. Firstly, it is worth to think if APSS particle loss correction would be a reasonable thing to do prior to the inversion. If MPSS and APSS inlets are far apart, not accounting for particle losses in sampling lines, may result in errors estimating particle shape and density. For this reason, always keep APSS and MPSS sampling lines as short and vertical as possible. Second, it is up to you to play with shape and density parameters to obtain the best fit as long as the chosen parameters have a physical meaning. To force one shape and density parameter over the all-particle size range, simply use the same values as both minimum and maximum. Third, knowing the APSS detection efficiency could also help to obtain more accurate shape and density parameters. And last but not least, to obtain the most accurate wide-range particle number size distribution, please do measure actual particle shape and density, as well as take into consideration all previously mentioned tips.